Yes, sir.
Yes, sir.
Yeah. So in this session, we'll continue with the dimensionality reduction. So in the last session, we were discussing the principal component analysis, right? So in this session, we'll continue with the dimensionality reduction and discuss the Fisher's linear discriminant analysis. So we'll also discuss the multiple discriminant analysis. That is basically when there are more than two classes, we will go for the multiple discriminant analysis. Whereas the linear discriminant analysis is for this two-class classification problem, right? So we'll continue with what is the disadvantage of PCA and why do we need this linear discriminant analysis. So what are the drawbacks of this principal component analysis and why do we need this linear discriminant analysis is the question that we are addressing first. So let us see an example. Okay, so if you remember the principal component analysis, it is always trying to project the data onto a space where there exists a maximum variance and a minimum error, right? So the direction of the maximum variance and the minimum error may not be useful for the classification all the time. Like you see this example, there are the instances from the two different classes. So if you project the data onto a direction of the maximum variance, it may project onto this direction, somewhere this direction. See that when you project the data points onto this direction, you see that there is a mix of data points here, right? It means the points are overlapped in the lower dimensional space. So as they're overlapped, there is no clear separation between them and it is difficult to classify them or learn a classifier that separates the instances of one class with the instances of the other class, right? So this is the problem with the PCA, principal component analysis. So principal component analysis is projecting the data onto a space where there exists a maximum variance, but the direction of the maximum variance may not be useful for the classification all the time. So here is an example for that. So suppose if you have projected this data onto a direction of maximum variance, it means this direction. So there will be a mix of data points from both the classes as you see in this case. So the instances are not separable. That is the problem with the principal component analysis. So have you understood this part? What is the drawback of the principal component analysis? Everybody? No? Hello? Are you there? Am I clearly audible?
Sir.
Yes.
I didn't get it.
Ramya madam, your voice is very low. I couldn't hear it. Following, right?
No, sir.
Not following? Should I
Yes, sir.
repeat?
I couldn't get it, sir.
Okay, okay.
Can you repeat, sir?
Sure. Do you recollect the principal component analysis that we had discussed in the previous class?
Yes, sir. Yes, sir.
So which direction is it projecting? Direction of the maximum variance and the minimum error. Am I right?
Yes, sir.
So it is projecting the data points onto a line where the variance is maximized and the error is minimized.
It is minimized. Yes, sir.
Yes. So suppose if I do that, right? So the direction of the maximum variance and the minimum error may not be useful for the classification problem. So here is an example I am giving. So here we have the data points from the two different classes. Each class is indicated with a different color and shape. So these are all instances belong to class 1. These are all instances belong to class 1. These are all the instances belong to class 2. Let's say that. Suppose if I choose a direction of the maximum variance and the minimum error for this example, then it may project the data points onto this direction where the variance is maximized and it means the spread is maximized as well as the error is minimized between the line and this data point. Am I right, madam? Everybody?
If it is middle of it, then it will be lesser.
Yes,
No, sir.
somewhere, doesn't matter. Okay, yeah, something like this.
Okay, yes, sir.
Yeah, yeah. So now when you project the data points onto this line, what will happen? This point will be projected here. 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 This point will be projected here, and so on. It means you may get a line something like this. I mean, projection something like this when you see it in the one-dimensional space.
Yes, sir.
Right. So you see that there is a no clear separation between the red points and the green points. Hello. Have you noticed that there is no clear separation between class 1 and class 2? Whereas if you see the original space, there is a clear separation. When you're projecting the data onto one-dimensional space, there is no clear separation between them. So it means what? You may not be able to learn a classifier that separates the red instances with the green instances, class 1 instances with the class 2 instances.
Yes, sir.
Right. So that is what the problem is. So the principal component analysis chooses a line of a direction of the maximum variance and the minimum error. But the direction of the maximum variance and the minimum error may not be useful for the classification because you're not considering the class labels when you're making the projection. You're just considering the direction of the maximum variance and the minimum error, that's all. But this direction of the maximum variance and the minimum error may not be useful for the classification. So have you understood the disadvantage of the principal component analysis as
Yes,
far
sir.
as
Now got it. Now got it.
yeah,
Yes.
yeah, classification problem is concerned? You see that? So this is the projection of the direction of the maximum variance and the minimum error, and that is may not be useful for the classification. So this is a bad line to project to, and the classes are mixed up in the lower dimensional space. Whereas if you choose this direction, you see that after projecting the data points onto one-dimensional space also, there is a clear separation between the projected data points. So this is a good line to project to class, and the classes are well separated even in the one-dimensional space. Okay, so that is the idea that the Fisher's linear discriminant analysis is trying to model. So we want to project the data points onto a line so that the samples from the different classes are well separated in the lower dimensional space. Classes from the two different classes are well separated in the projected space, right? So that is what we want to do. Clear? The idea is clear, right? So before we're going to see the notation, is the idea clear what we are trying to do?
Sir, is that the point? So next before slides.
Is it the problem with me? Okay, wait a minute, madam. Let me increase the sound. Yeah, please speak up, madam.
Sir, the before slides.
Ah.
So in this, we are having it on left side. We have both in red and green on the separate direction, no, sir. How this is coming in the same direction, sir?
Which one? Red and green
Right.
on.
Right side we are getting separately, no, sir. How it is?
Right. Okay, okay. So you're saying that how on the same line? How are we getting this line?
Yes, sir. That green and red, it is coming in the same line, no, sir.
Because you're projecting that onto one-dimensional space, right? Onto this line. This is a one-dimensional data. I didn't get your point.
This blue line is the projection line now, sir.
Yes, yes.
Okay, sir.
Similarly here also, it is the projection line. This is a bad line. This is an example of the bad line. This is an example of the good line as far as this classification problem is concerned. You know the reason. Why? Why is it a bad line? Why is it a good line?
Red and green are in the separate direction.
So in this line, when you project the data points, the classes are mixed up. Points from the two different classes are mixed up. They are not well separated. Whereas if you project onto this line, classes are well separated even in the projected space. That's why it is a good line to project. That's what we're saying, right? So now the objective is to learn a direction where the classes are well separated. Clear, madam?
Yes, sir. Now I got it.
Yeah. Everybody following?
Yes, sir.
Yes, sir.
Fine. Geeta ma'am, is it clear? Yash?
No,
Lavish,
actually, I joined
Lavish.
when you were in the slide showing when the data is in the multi-dimensional and when the data is in the single dimensional.
No, madam, don't worry about that. Very simple. You remember the principal component analysis, right? Which we discussed in the yesterday's class,
Yes,
previous
yes.
class. So which is projecting the data points onto a direction of the maximum variance and the minimum error. So if you project the data points onto a direction of the maximum variance and the minimum error, that direction may not be useful for the classification. And this is an example for that. You see that when you project the data points onto a direction of the maximum variance, the instances from the two different classes are mixed up and they are not clearly separable. Whereas if you see this line, if you project the data points onto this line, they are well separated, right? So the summary of this is that the direction of the maximum variance may not be useful for the classification. So therefore, you need an alternative measure so that the projection of the data points in the lower dimensional space also well separated. It means the idea is to learn a line where the instances in the projected space also well separated. That's the idea that we are trying to look into. Clear, ma'am? Is that clear? Is that clear, ma'am?
Actually, that line is a principal axis only, no, sir?
Which one? This one. This one is the
Second line.
principal axis, first one. Second
Which
line,
one, sir?
no, first one is the principal axis where you are projecting the data point onto a line of maximum variance.
Yes.
That may not be useful for the classification all the time. The instances might mix up in some cases, like this case. Okay. Is the idea clear to everybody? Shall we move on?
Yes, sir.
Yeah, fine. So the next one, we'll see the notations first, then we'll see how to learn this line so that the classes are well separated in the projected data space. Okay. So let's say that we have two classes and d-dimensional samples. So there are n instances. Each one of the instance is described in the d-dimensional space, d attributes. And there are two classes, class 1 and class 2. N1 number of instances are from class 2 and N2 number of instances are from N1 number of instances are from class 1 and N2 number of instances are from class 2. So therefore total number of instances N equal to N1 plus N2. So N1 of them are belong to class 1 and 2 of them are belong to class 2. Okay. So consider there is a line whose direction is given by a vector V. Right. Suppose if you are trying to project this data point xi onto a line whose direction is given by V, right? So to get the point in the projected space, what we do is that we multiply this V transpose with xi. So this V transpose xi is the distance of the projection of xi from the origin. It means basically it is giving you the projection of xi onto one-dimensional subspace. So in simple words, if xi is the original point, V transpose xi is the projected data point. It means if you are projecting xi onto a line whose direction is given by V, the projected point is V transpose xi. So if xi is the original data point, if you are projecting this xi onto a line whose direction is given by a vector V, then V transpose xi is the point in the projected space. Clear? That much is clear. V transpose xi.
Yes, sir.
Right. So now the original data points are x1, x2, so on, xn, and projected data points are V transpose x1, V transpose x2, so on, V transpose xn. Now the task is to learn this line direction so that the classes are well separated in the projected space also, right? So can you tell me what is a good measure of separation between the classes? How can you judge that two classes are well separated in the projected space? If their centroids are far away from each other, can I say that they are well separated?
Yes,
Yes, sir.
that can be one of the.
One of the criterion, right? Definitely.
Yes,
Right.
yes,
So if the centroids of the two classes in the projected space are well separated, it means if the distance between the centroids of the classes in the projected space are well distanced from each other, then we say that these classes are well separated. Okay. So, but how do you compute the centroid? Tell me, how do you compute centroid in the original space? If x1, x2, so on, xn are the so this here in the slides, x subscript I use it for the instance I, but because of my regular usage, I am just using x superscript I. Please don't confuse with that. Okay. So now let us say that x1, x2, so on, xn are the points in the original space, and there are n1 instances belong to class 1 and n2 instances belong to class 2 from this n instances. So now I am asking you to find out centroid of class 1 and centroid of class 2 in the original space. How do you compute that centroid of class 1 and centroid of class 2 in the original space? Suppose if I want the centroid of the class 1, let us call it as a mu1. How do you do it? 1 by n1, take all the instances that belong to class 1. For all xi belongs to class 1, for all xi belongs to class 1, take sum over xi. Sum over xi, right? So isn't it the centroid average of all the instances belong to class 1 is the centroid of class 1 in the original space. Am I right? Hello? So please do
yes,
respond.
yes.
Yeah. So
Then
this
what
is the centroid of class 1. Similarly, can you find out the centroid of class 2? What is mu2?
1 by
1 by n2.
N2.
sigma of
Sum over
All xi belongs to
x2.
class 2
C2
Class 2.
xi,
x2. Xi.
right? So
Yes.
basically you are taking average of all the instances belong to that class, that gives the centroid of that. So this is the centroid in the original space. Now suppose if I want to find out the centroid in the projected space, because we want the centroids to be well separated in the projected space, not in the original space. All right. So we want these centroids to be well separated in the projected space. It means let us try to compute the centroids in the projected space. So what are the points in the projected space? V transpose
xi.
x1, V transpose x2, so on, V transpose xn, right? So can you compute the centroids in the projected space? Let us call it as a mu1 bar. So this is 1
Instead of
by
xi, use v transpose.
use V transpose xi, right? So for all xi belongs to class 1. Now instead of xi, we are taking V transpose xi, right? Similarly, can you tell me mu2 bar? Mu2 bar is 1 by n2.
n2.
Sum over xi belongs to class 2 V transpose xi. Okay. So now let us try to derive the relation between the mean or the centroid in the projected space and the centroid in the original space. So please see that this is the mu1 bar, which is the centroid in the projected space. So 1 by n1 sum over xi belongs to C1 V transpose xi. So now if you bring this V transpose outside the summation, this will be equivalent to V transpose 1 by n1 all xi belongs to C1 xi. So what is this? Can you identify what is it? Isn't it the centroid in the original space?
Mu1.
Mu1, right? So centroid in the projected space is equivalent to V transpose times centroid in the original space. Centroid in the projected space is equivalent to V transpose times centroid in the original space. Similarly, mu2 bar is equivalent to V transpose times mu2. Hello, are you with me so far?
Yes, sir.
Yes. So this distance between, it means mu1 bar minus mu2 bar should be maximized. It means we have to learn this V in such a way that this distance is maximized. This is the objective, right? So, but there is one problem with this objective alone, right? So here you see that now we want to see how good is this distance between the centroids as a measure of separation. So can we always say that if the distance is more, then the classes are well separated? Can we always say this, right? So let us see an example. So here, this is the data, and suppose if I project the data points onto x-axis, you see that these are the means in the projected data space, right? See that the distance between them, let us call it as a d1, okay? And you see that there are some mix of data points. It means the instances are overlapped in this direction. Whereas suppose if you project this data points onto the direction of y, and this is the, let us call the distance as a d2, and here the classes are well separated. Please look at this figure and tell me, is d1 greater than d2 or d2 greater than d1? Which distance is more?
D1.
D1.
D1 is more.
D1.
Right? But usually what we thought, if the distance is more, the classes are well separated. But this, what is this? This is contradicting with that assumption, right? So you see that here the distance is less, but the classes are well separated. Here the distance is more, still the classes are not well separated. So it means we are missing some point here, right? What is the point that we are missing? So in addition to the distance between the centroids, we also need to consider something else. What is that it is missing? Please observe both these cases and tell me what is the difference. What is the difference between them? Why the classes are mixed up even though the distance is more? In this case, why the instances from the two different classes are mixed up though the distance is more? Distance between the centroids are more. What is the reason? And or else you tell me why the classes are not mixed up here although distance is less. Tell me what is the reason. Yes, madam, please go ahead.
Direction, sir.
No, direction anyhow you can choose any direction. Why is
The
that?
horizontal line, due to horizontal lines,
No, any direction. How does it?
horizontal direction.
No, it's not about horizontal or the vertical direction. Just tell me, look at, observe the spread of the data points in the projected space. How the points are spread in the projected space in both the directions. Individually, you look at
Horizontal more spread,
horizontal more spread and vertical it is
less.
less spread. It means what?
Variance.
The variance is more in this direction, whereas the variance is less in this direction. Isn't it? So it means what? In addition to maximizing the distance between the centroids, we also have to minimize the variance within each class. You see that all the class 1 points are spread in very small distance. Here also all the class 2 instances are spread around a small distance. So that's why these points are well separated. Here if you see, all the class 1 instances are spread in the more distance, as well as the class 2 instances are also spread in the more distance. So as a result, because of the spread, they are overlapping, right? So it means what? We have to also consider the variance along with the distance between the centroids. So one point is we want to maximize the distance between the centroids. Second point is we have to minimize the scatter within each class. It means points belong to one class must be spread within a small distance. We want to minimize the scatter within each class. This we want to do it for all the classes. Clear? Is that point clear?
Yes, sir.
Yes, sir.
Right. So the considering the distance between the centroids as an objective, I mean considering maximization of the distance between the centroids alone is not a good measure of separation. Right. So in addition to that, we also have to consider the spread of the data points or the scatter of the data points. So in addition to maximizing the distance between the centroids, our objective is to minimize the scatter within each class. Okay. So with this objective, let us formulate our objective function. Okay. So this is the problem. The problem with the mu1 bar minus mu2 bar alone is that it doesn't consider the variance of the classes. So if you see this, in this direction, we have the larger variance. In this direction, we have the smaller variance. So it means we need to normalize this mu1 bar minus mu2 bar by a factor which is proportional to this variance. All right. So let us try to compute the scatter of each and every class separately. All right. Scatter of the data points belong to a particular class. Right. So to compute the scatter is just a scale difference between the with the variance. So it means scatter is equivalent to n minus 1 times the variance. Okay. So both of them are same, just the scale difference. Scatter equal to n minus 1 times the variance. All right. So to compute the scatter, how do you compute the variance? Do you remember how do you compute the variance? Expectation of x minus e of x whole square. Am I right? Do you remember the variance formula? Expectation of x minus e of x whole square. Hello?
Square
Right.
of the
Right. So it means what? You are taking each and every point, subtracting it from the mean and taking square of that. Right. So there you take the average. Here you just take the sum over. Sum over I equal to 1 to n zi minus mu z whole square. Where zi is the individual sample, mu z is the mean of that samples. Okay. So this is how we compute the variance. Okay. So variance is, so scatter is just a sample variance multiplied by not n minus 1. For variance we take 1 by n minus 1, not n. All right. So the scatter is measures the same thing as the variance, which means the spread of the data points around the mean. Okay, but it's just a scale difference with the variance. That's all. So this is an example of a larger scatter. And this is an example of the smaller scatter, because the scatter or the variance measures how the points are spread around the mean. You see that on an average, the distance between the squared distance from the centroid to the points is more in this case as compared to this case. That is why the scatter is more in this case, the scatter is less in this case. Okay. So have you understood how to compute the scatter? Have you understood
Yes.
how to compute the scatter? Okay. So if you have understood this, what is our objective? Our objective is to minimize the scatter within the class. Okay. So can you tell me how to compute the scatter within class 1 and how to compute the scatter within class 2? All right. So let us just try to do that. So we have points like x1 in the original space we will do, later we will do for the projected space. So x1, x2, so on, xn are the points, and one of them belongs to class 1 and n2 of them belongs to class 2. Okay, I want you to find out what is the scatter of class 1. What is the mean of class 1? Do you remember in the original space we gave name called mu1, right?
Yes.
Right. So now the scatter is subtracting the mean from every point belong to that class, isn't it? So let us say S1 is the scatter of the class 1. How do you compute? Take sum over all xi belongs to class 1. What we have to do? x1 xi minus mu1 whole square. Am I right? Isn't it the scatter? According to this definition. Hello everybody, following or not? Ramya madam,
Yes, sir.
Yes,
Following,
yes,
sir.
what? Sophia ma'am,
Yes, sir. Following, sir.
yeah. Everybody else, sir Paramesha sir, Ravi sir,
Yes, sir.
Yes, sir. Yes, sir.
okay, fine. So now can you tell me how to compute the scatter of class 2?
sigma x2 of xi of c2.
Sum of
X1,
C2?
X2 belongs to C2, Xi minus
x2 minus
mu2 whole
mu2.
square.
whole square.
Okay, this is scatter 2. So this is the scatter in the original space. How do you compute the scatter in the projected space? Can you tell me? Let us say it is S1 bar and S2 bar. How do you compute the scatter in the projected space? Sum
Sigma
over all xi belongs to C1. Instead of xi, we take
v
Y.
transpose xi minus
minus mu1
mu1 or mu1 bar.
mu1 bar.
Mu1 where?
Mu1 bar. We have to take mean in the
mu1
projected
bar.
space. All right. Similarly, S2 bar is equivalent to sum over all xi belongs to class 2 V transpose xi minus what is it?
Mu2.
Mu2 bar
Bar.
Whole square.
Bar. Whole square.
whole square. Right. That's what it is doing here. So here yi's are taken as the projected samples V transpose xi. All right. So now this scatter is indicated with S1 bar whole square in the scatter of class 1 in the projected space, which is for all yi belongs to class 1, yi minus mu1 bar whole square. So where yi is V transpose xi. It's the same thing, right? Similarly here, for all xi belongs to class 2, it is V transpose xi minus mu2 bar. So V transpose xi, here it is given as a yi. That's all. Here you see, yi is V transpose xi. All right. So now we understood what is the scatter in the original space, what is the scatter in the projected space. So now let us try to derive a relation between the scatter in the original space and the scatter in the projected space. All right. So before that, let us also try to understand what is our objective. Our objective is what? Our objective is to maximize the distance between the centroids in the projected space. Am I right? So it means we want to increase the distance between mu1 bar, maximize the distance between mu1 bar and mu2 bar in the projected space. In addition to that, what we want to do? What is the other objective? Minimize
Scatter.
scatters in the projected space. It means this S1 bar square plus S2 bar square we want to minimize. Hello, am I right? We
So
want to max.
why square S1 square?
That is some just notation, madam, because here square is given, there's given a square, some notation. But if you want, you just give S1 bar also, it doesn't matter.
Okay, sir.
Some notation, yes. Okay. So is it clear? The objective is to maximize this and minimize this, isn't it? So instead of solving the two objectives, can I formulate it as a single objective? So maximizing this is equivalent to minimizing 1 by this. Sorry, minimizing this is equivalent to maximizing 1 by this one. S1 bar square plus S2 bar square. Hello, am I right? Minimizing this is equivalent to maximizing this. Okay.
Yes.
So now can I write it as a maximization of mu1 bar minus mu2 bar divided by S1 bar square plus S2 bar square? The single objective, both the objectives will be taken care, right? With this. Hello, everybody, understood this?
Yes, sir.
Yes, sir.
Yeah, great. So this is what is our objective. It means we want to project the data points, or our goal is to learn the direction V that maximizes the difference between the projected means and minimizes the scatter within each class. It means we want the projected means are far from each other, and we also want the scatter within class 1 and the scatter within class 2 is as small as possible. Okay, so it means we want to have these points in the projected space spread around its mean only. It means within a small distance we want to scatter them in the projected space. It means we have to learn this line direction V where the centroids are well separated and the scatters are minimized. Okay, so this is what is our objective is. This is what is our cost function that we want to maximize, not minimize. All right. So is it clear? So far, the objective is clear.
Yes, sir.
Have you understood why we have got this objective J of V? Everybody clear, right?
Yes, sir.
Yeah.
Maximizes
So,
both.
yeah. So we want to find out V, which makes J of V larger. Then we are guaranteed that the classes are well separated in the projected space. So whenever J of V is larger, the classes are well separated. Obviously, because what we are trying to achieve, we want to project the data points such that the means are well separated and the scatter is as small as possible. So obviously, the classes will be well separated if we achieve both these objectives. All right. So we are guaranteed that the classes are well separated. So now try to derive a relation between this scatter in the projected space and the scatter in the original space. So let us take a scatter in the original space. So this is sum over all xi belongs to class 1, xi minus mu1 whole square. Okay, so in the vectorized notation, this can be written as xi minus mu1 times xi minus mu1 transpose, right? So if there is a multi-dimensional data, instead of taking this, you can directly take xi minus mu1 times xi minus mu1 transpose. So this is same as that. Okay, both of them are same. Similarly, S2 equivalent to xi minus mu2 times xi minus mu2 transpose. Both of them are same. So now let us take the within class scatter matrix. So within class scatter matrix is the distance within each class, right? We want to minimize this. So we want to minimize SW, which is within scatter of class 1, within scatter distance of class 1, within scatter distance of class 2. So this we want to minimize for both the classes together, S1 plus S2. So now recall that this S1 bar is equivalent to this V transpose Xi minus mu1 bar whole square, right? So this is equivalent to V transpose Xi minus V transpose mu1, because we know that mu1 bar is equivalent to V transpose mu1, right? And Yi is equivalent to V transpose Xi. So if you expand this, this is equivalent to, let me write it here. This is equivalent to V transpose Xi minus V transpose mu1 times V transpose Xi minus V transpose mu1 transpose, as per the previous slide. Take the V transpose common, both the sides, you will get this V transpose Xi minus mu1, V transpose Xi minus mu1 transpose. Okay, so is it clear? Are you with me so far? Till this point. Is it clear? Or should I repeat? Please say something. Whatever it is, okay. But
Splitting them and writing in a square, isn't it, sir?
yes. So we're just writing it in a different notation, like the way we have written here, no? Xi minus mu1 bar whole square is equivalent to Xi minus mu1 times Xi minus mu1 transpose in a vectorized notation. That's what we have written here, right? So similarly, we are writing the same thing here also. V transpose Xi minus V transpose mu1 times V transpose Xi minus V transpose mu1 transpose. So similar to the way that we have written, no, Xi minus mu1 times Xi minus mu1 transpose. So here instead of Xi, we are writing V transpose Xi. Instead of mu1, we are writing V transpose mu1. The same thing. This is in the original space. This is in the projected space. Clear? Not following? Should I repeat?
No, sir, we are following.
Following. Okay.
Yes, sir. Following.
Yes. Thank you. So now AB whole transpose. What is it? When you expand B transpose times A transpose. Am I right?
Yes, sir.
Right. So if you expand this, what will you get? You will get Xi minus mu1 transpose times V transpose to the transpose. So which is equivalent to Xi minus mu1 transpose times V?
Yes, sir.
Right. Yes.
Yes, sir.
So this is V. So when you expand this, you will get this Xi minus mu1 transpose times V. This is anyhow it is there. V transpose Xi minus mu1. Okay. So what is this? Xi minus mu1 times Xi minus mu1 transpose. Isn't it S1?
S1.
Right.
S1,
So
sir.
substitute, yes. V transpose S1 times V, which is V transpose S1 times V. So this is the relation between scatter in the projected space and the scatter in the original space. So this is the scatter in the projected space and this is the scatter in the original space. Got it? So S1 bar is equivalent to V transpose S1 times V. So can you tell me what is S2 bar then?
V transport
Go on, ma'am.
S2V.
S2V. And what is the within scatter? SW bar, which is S1 bar plus
Plus
S2 bar.
S2 bar.
So which is equivalent to V transpose S1 times V plus V transpose S2 plus times V. And this is equivalent to V transpose SW times V. Alright, so that's what it is given here. So S1 bar plus S2 bar is equivalent to V transpose S1V plus V transpose S2V. Right. So this is the, by expressing it in terms of the original scatter. S2 bar by expressing it in terms of the original scatter. So because S1 plus S2 equivalent to SW, this is equivalent to V transpose SW times V. This is what we want to minimize, the denominator part. And between class scatter, which is basically this mu1 minus mu2 whole square, right? So this can be written as mu1 minus mu2 times mu1 minus mu2 transpose, which is between class scatter. Between class scatter, it means the distance between the means. All right. So this we want to maximize. All right. So what is this mu1 bar minus mu2 bar? This is mu1 minus mu2 whole square, which is in the original space. So what is mu1 bar minus mu2 bar whole square? When you expand this, this would be V transpose mu1 minus V transpose mu2 whole square. And when you expand it further, V transpose times mu1 minus mu2 times mu1 minus mu2 transpose. So how is this looking like now? Isn't it the between class scatter distance in the original space? Right. So substitute that SB. So V transpose SB times V. So basically this is a very simple, although it may be confusing. Let me clear it off at this point itself. So there are two things that we are talking about here. If this is class 1, if this is class 2, one thing that we are talking about is distance between the centroids. This we are calling it as a SB. Okay, SB in the original space and SB bar or whatever that you call mu1 bar minus mu2 bar whole square in the projected space. Do we have to maximize this or minimize this between class scatter?
Maximize this.
Maximize.
Maximize. This we also call it as a inter-class distance. Inter-class distance or between class distance, between class scatter, SB, right? This we want to maximize. The second thing that we are talking about is within class scatter. It means within this class, what we want to minimize or maximize?
Minimize.
Minimize. That we are calling it as a SW. But this we want to do it in the projected space, not in the original space, right? That is why we are expressing this in terms of the projected data points, and the projected data points are expressed in terms of the original data points, because what is given to us is original data point only. We don't know what is the projected data point, right? So you have to find out line direction V so that this projection can happen onto that line, right? But until you find out that line direction, we don't know what it is. So that is why you are expressing this in terms of the original data points only, right? So this is the between class scatter in the original space. Mu1 minus mu2 times mu1 minus mu2 transpose. This is the distance between the centroids in the projected space. So this you are expressing it in terms of the original data points. So the distance, the squared distance is equivalent to V transpose SB times V, and this is what we want to maximize. Clear? Is this point clear? And within class scatter also, this is the projected data points within class scatter, and this is the original data points within class scatter. So the relation is this is equivalent to V transpose SW times V. So have you followed this point?
Yes, sir.
So if you have followed this in I mean, you take these two, V transpose SWV and V transpose SBV. What you want to maximize and what you want to minimize.
SW minimize, SB maximize.
So V transpose SBV we want to maximize, and V transpose SWV we want to minimize. It means, can I write it as a V transpose SBV divided by V transpose SWV maximization?
Why we have to write like that?
Achha. Understood.
I'll tell you. This you want to what? You want to minimize, right?
Yes, sir.
This
Yes.
you want to maximize.
Yes, sir.
Minimizing this is equivalent to maximizing 1 by this. Am I right?
Yes.
Minimizing f of x is equivalent to maximizing 1 by f of x, or maximizing f of
Yes,
x
sir.
is equal, right? Using this, I can write minimizing this is equivalent to maximizing 1 by V transpose SWV. So now both are the maximization problems, so we can solve them together. We want to maximize V transpose SBV divided by V transpose SWV. Clear, madam?
Clear, sir.
Right. So this is we want to maximize V transpose SBV divided by V transpose SWV. So our objective now is find out V such that this is maximized. So what is the parameter of our objective function? Parameters of our objective function is V. V is what? The line direction. Where to project is the question, right? So in which direction the classes are well separated is the question. So we're just trying to formulate that objective. So if you solve this direction, if you solve this objective and choose a V or a direction V that maximizes this objective, then you are done. You'll be identifying a line of a maximum separation between the classes and a minimum scatter within the classes. It means if you identify such direction V, the classes are well separated in the projected space when you're projecting them onto that line whose direction is given by V, right? So the task is to identify that line direction V. That's all. Got it? Is it clear now so far? Whatever that we have discussed, we're just trying to formulate the problem as a mathematical function, then we solve that. Hello, everybody clear?
Yes, sir.
Sir. Yes, sir.
Yes, sir.
So this is a maximization problem that you want to maximize, and this is like this, and optimal point is this, right? So what is the slope of the function at the optimal point?
0.
0. This is j of v and this is v, and the slope of the function at the optimal point is 0. And how do you get the slope? Derivative of j of v with respect to v, you will get the slope. So if you want to get the optimal point, take the derivative of j of v with respect to v and equate that to 0. Okay, so this is our j of v. So take the derivative of this with respect to v. All right. So when you take the derivative of this with respect to v and equate that to 0, you will get the optimal point. Okay. So do you remember what is the derivative of u by v with respect to x? Formula: v times derivative of u minus u times derivative of v divided by v square. Am I right? Isn't it the formula? Right?
Yes.
So now apply the formula for this. What is v? What is u in this? V is this and u is this. Don't confuse between this v and that v. Okay. Okay. I hope you understood what, or I will give different names here. Is it okay? Would you understand?
Okay, sir.
Yeah. So this is v transpose SWV times derivative of v transpose SBV and minus derivative of v transpose SWV times v transpose SBV divided by this v transpose SWV whole square. Okay. So when you solve this, you will get this. Are you with me so far? Following? A bit of mathematics here, but if you understand, you will enjoy this.
Sir,
Madam.
we have numerator VT and denominator VT. Can't we cancel it, sir?
Where, madam? V transpose SWV.
JV, sir. In numerator also we have V and
JV, this one. So basically, madam, if they are scalars, you can cancel, but they are not scalars all the time. Okay. Somewhere you will see that they are scalars. Then you can directly V transpose, you can cancel, madam, because they are vectors. They are not the scalars. Okay. Fine, madam. Whenever they're becoming scalars, you can cancel, and that too if it is required. If you want to, I mean, if it is simplifying the problem, then only. But our objective is different here, right? Our objective is to find out V, not just to solve this J of V. So we want to choose a V that is optimizing this J of V, right? So we have to proceed in that direction. How can I find out V such that this is maximized? That is our objective. Clear, madam?
Yes, sir.
Yeah. So now, so can I take this other side? Right? I can take it, right? So when you take it the other side, you will get this V transpose SWV times SBV minus V transpose SBV times SWV is equivalent to 0. Okay. So now let me divide it with V transpose SWV. Hello, I hope you're following. Please reply to me, because even if you don't follow one step, it is difficult for you to follow the rest. So you took this derivative and you take this the other side, you've got this 2 also, you got that side, you got this. Now you are dividing everything, both the sides, LHS and RHS, by V transpose SWV. Clear? Till now it is clear?
Yes, sir.
Yeah. Now you see this. V transpose SWV. This is a scalar. Okay. So because this is of some 1 by d and this is of d by d and this is d by 1. So altogether some 1 by 1 you are getting, which is a scalar, right? So now It's a scalar. So therefore, this and this get cancelled. You will get 1. Okay. And this also scalar. V transpose SBV divided by V transpose SWV is also a scalar. But this is not equivalent to 1 because this is different. This is some scalar. Let us call this as a lambda. Okay. So this is equivalent to SBV minus some lambda times SWV, which is equivalent to 0. When you bring the other side, you got SBV is equivalent to lambda times SWV. Alright, so this is looking like a generalized eigenvalue problem. Okay, so let us convert it into an eigenvalue problem. What is eigenvalue problem? If AX is equivalent to lambda x, then we call lambda as a eigenvalue of x, a as a eigenvector of x. No, I'm sorry. X is the eigenvector of a, and lambda is the eigenvalue of a. Am I right? Hello? Eigenvalue problem. Do you remember? If ax equivalent to lambda x, we call x as the eigenvector of a, lambda as the eigenvalue of a. Hello? Am I right?
Yes, sir.
Yes.
A is the eigenvector.
No, x is the eigenvector. Eigenvector of a.
First you told A as vector, sir. Acha.
No, first I told I corrected it. That's what I'm
Okay.
saying. Yeah. I corrected it. Yes, that's wrong. What I said is wrong. So x equal to lambda x, then x is the eigenvector of a and lambda is the eigenvalue of a. Right?
Sir,
So,
so that lambda only is the JV, no, sir? The previous slide.
lambda is not JV, madam. Lambda is zero only, not in the previous slide.
Scalar.
Lambda is some scalar value. Some scalar. It doesn't matter to you. Some scalar, some value. You want me to go to previous slide?
Yes, sir. In the JV slide, we saw like.
How does the differentiation of V transpose SBV over DV, sir?
No, I just gave some variable d, sir, but that is like, see, this is like.
No. First term in the numerator, sir. D dou by dV, sir. The first term.
This one.
V transpose. Yeah, how this is solved? Because 2SB you are getting. How it is solved?
Sir, here this is of the form some let's say m by n. Okay. So what is the derivative of m by n with respect to x? This is n times derivative of m minus m times derivative of n divided by n square. This is the general formula, sir. I'm not doing anything here. This is the general formula.
No, sir. I'm specific with respect to the differentiation of DT that is
This
V
one,
transpose
with respect
SP.
to
Yeah,
V.
only that term, sir.
Yeah,
that
this
term
is like you can see it like a V square, na, sir. V transpose V is there. I mean, usually with respect to vectors, how you solve this derivative is, sir, you'll be expanding them with respect to each and every element and taking the derivative and then taking that back to a vectorized format. Okay.
yes,
So
sir.
you can see it like there is a
yes,
V
sir.
square term in that. When you take the derivative of this, because V transpose V is there now, sir, in this. So you will get somewhere V square. So when you take the derivative of V square with respect to V, you will get it to 2V. So that is why you got 2 times SBV here. But this I will not say that directly you are doing this, but when you expand this element wise, this is happening. And when it happens element wise, when you converted that back to a vectorized format, you will get this 2 times SBV.
Okay. Sir,
Clear,
why
sir?
can't it be 2 times VSB? Is there any
That is,
difference?
that's what I'm
Okay.
telling you, sir, that
Okay.
when you expand this, when you expand this and solve it element wise derivatives,
Okay.
whatever you get, that is what. It's not either v times SB or SB times V. So whatever is that you are getting in that element wise, when you express it in terms of the vectorized notation, whatever is you are getting, that is what we write here.
Okay. No problem.
Yeah.
Okay.
I hope that is clear, sir. Is any further query there? Clear? Okay. So all right. So now, so this is the generalized eigenvalue problem. So now, can I write it as a? Can I multiply it with SW inverse both the sides? SW inverse times SB times V lambda times SW inverse times SW times V. And what is this SW inverse SW? What is A inverse A? Yeah, I, right? Identity matrix, I. And anything multiplied by I is that matrix, right? So this is equivalent to lambda times V. So SW inverse SBV is equivalent to lambda times V. Isn't it in this form? A times X is equivalent to lambda times X. Hello, isn't it the form? So what is A? What is V here? What is X here? This is A and this is X. So it means what? V is a eigenvector of this SW inverse SBV. So if I compute the eigenvector of SW inverse SBV, will I get the optimal V? Hello?
One
Lost.
second.
Yes, sir.
Okay. yeah, sure, madam, sure. So I know that this is slightly difficult term, so let me repeat. So till here, have you understood, Ramya, madam?
Yes, sir.
Yeah.
Yes,
yeah.
sir.
Yes. So now I'm multiplying it with SW inverse both the sides. Can I do that? SW inverse, SW
Yes, sir.
inverse. Okay. So now this is SW inverse times SW. What is it? A inverse times A? It's an identity matrix.
Identity
Right?
matrix.
So this I am replacing it with identity matrix. And anything multiplied with identity matrix is equivalent to that. So I times V is equivalent to V. Am I right, madam? So
Yes,
this
sir.
is what I get. SW inverse SB V is equivalent to lambda times V. This is the eigenvalue problem. Okay. It means here when you are saying this, you are indirectly saying this or directly only saying this. V is the eigenvector of what? SW inverse times SB. Am I right? Because it is of the form A times X is equivalent to lambda times X. Right? Where X is the eigenvector of A. So what is A in this? SW inverse SB. Am I right, madam?
Yes, sir.
Yes, sir.
So it means if you can find out the eigenvector of SW inverse SB, that is the optimal V that you are looking for. Am I right? You are solving for the optimal V only, right? So far. Don't forget that. Forget the base. Don't forget the base. Base is what? You want to find out an optimal line direction where the classes are well separated in the projected space. That's what you're solving for. And you have formulated it like this. So learning a line direction where the classes are well separated is equivalent to maximizing this V transpose SBV by V transpose SWV. And the optimal point you are getting when the slope is equivalent to 0. So you are taking the slope. It means the gradient of the J of V with respect to V and equating that to 0. When you solve this, you got this eigenvalue problem. It means solving this eigenvalue problem, you will get the optimal V, right? Where the classes are well separated in the projected space, right? So it means if I can identify the eigenvector of this SW inverse SBV, that is the optimal V. Clear? So far, are you with me?
Yes, sir.
Yes, sir.
Yes. Cool.
Yes, sir.
Okay, this is one. Okay, now that we have brought it to this stage, this is one solution definitely that you can directly compute the eigenvector of SW inverse SBV, and that is the optimal way. Okay, but you need not even do that much also, because we have some other relation. Using that you can simplify it further. Okay, so let us see what is that relation and how do we simplify it further. Okay, so you need a little more attention, okay, to understand this. I'll repeat it twice, but try to understand it. Okay, even if you don't understand, it's okay, don't worry about it, because till now you have understood. So this is the problem that we have got. SW inverse SBV is equivalent to lambda V, and we said that if you can identify the eigenvector of SW inverse SBV, that is the optimal V. All right. So now we identified one property with SBX, SB, which means the between scattered matrix. Right, to simplify it further. So what is that property? Let us have a look at it first. Okay. What is SBX? SBX is this mu1 minus mu2 bar, mu1 minus mu2 whole square, isn't it? Mu1 minus mu2 whole square. It means mu1 minus mu2 times mu1 minus mu2 times mu1 minus mu2 transpose. This is SB. Right, SB times X. All right. So this mu1 minus mu2 transpose times X, mu1 minus mu2 transpose X. So this is of 1 by D and this is of D by 1. So this is 1 by 1. It's a scalar. So can I write it as a scalar? Alpha, some alpha is a scalar, right? 1 by D times D by 1 is a scalar. It's a alpha, right? So any vector X, for any vector X, when you multiply it with SB, you will get alpha times mu1 minus mu2 for some scalar alpha. Agree? Hello? Agree?
Yes, sir.
Right. So for any vector X, when you multiply that vector with SB, you will get alpha times mu1 minus mu2 for some alpha. Alpha is some scalar. So it means what? This is in the same direction as mu1 minus mu2. They are just some magnitude difference, that's all. They are in the same direction. So it means for any vector X, it points, SBX points in the same direction as mu1 minus mu2. Agree? For any vector X, SBX points in the same direction as this mu1 minus mu2. This is what the property of this SB. Okay. So now for which vector I should take SB? All right. Sorry. For which vector V this happens? For which vector V for which vector V this SW inverse SB times V is equivalent to lambda times V. It means if I take which vector in place of this V, this is equivalent to some scalar times V, some scalar times lambda or alpha, some scalar times V is the question. Okay, so that happens only for this SW inverse mu1 minus mu2. You can try that also. So when you substitute V equal to SW inverse mu1 minus mu2, so what happens? This SW inverse mu1 minus mu2. So this is some vector V. What happens when you multiply SB with some vector? You will get some alpha times mu1 minus mu2. Am I right? So the whole thing can be replaced with what? Alpha times mu1 minus mu2. Am I right? Hello? Am I right? When you multiply SB with any vector, this is equivalent to alpha times mu1 minus mu2. So you can replace this whole thing with alpha times mu1 minus mu2. When you bring out this alpha, this is equivalent to SW inverse mu1 minus mu2. So, and what is SW inverse mu1 minus mu2? It's nothing but V. It means what? this is SW inverse SBV times V is equivalent to lambda times V is happening when V is equivalent to SW inverse mu1 minus mu2. It means what?
Yes.
You need not even solve the eigenvector problem of this SW inverse SB. You can directly compute V using this property. Okay, so let me repeat. For some of you, I know that some of you have understood, but for some of you, it is little bit confusion yet. So let me explain this one more time. So have you guys understood till this point so far? I hope this is clear. Till this point is clear. Everybody clear? Till then, till this point.
Sir, if we backtrack, we are able to understand, sir.
Okay.
First, we are replacing this one with V. Then we are replacing that with alpha. SB X, right?
Yeah, it's very simple, madam. See, there is one property for this SB. If you multiply this SB with any vector x, that points in the same direction as alpha times mu1 minus mu2. That's what we are proving here. So SB is this, mu1 minus mu2 times mu1 minus mu2 transpose. And this is 1 by d, this is d by 1. So if you multiply this any vector with this one, this will become a scalar. So this is some scalar alpha. So this is alpha times mu1 minus mu2. This is what the proof. Proof is complete. So SBX is in the same direction as mu1 minus mu2 because they're just some scale difference, nothing more, right? They're in the same direction. Both of them are pointing in the same direction, right? So now using this property, we are now asking for which value of V this happens. What happens when you multiply SW inverse SB with V? This is equivalent to some scalar alpha times V. So for which value of V this happens? Okay, so it happens only for this V, SW inverse mu1 minus mu2. That we are proving here, right? So when you substitute SW inverse mu1 minus mu2 in this, okay, this is some vector V. So when you multiply SB with V, what happens? Any vector V, it will be pointing in the same direction as mu1 minus mu2. So therefore, this whole thing is becoming alpha times, alpha is some scalar, mu1 minus mu2. Okay, so now if you bring this alpha the other side, this is alpha times SW inverse mu1 minus mu2. So what is that? SW inverse mu1 minus mu2. That is what the V that you have assumed. So this is equivalent to V. So is it happening or not? SW inverse SBV, this V is equivalent to lambda times V. So that is happening for this V. So can I say this is the optimal V? Hello, can I say that? Not followed? Should I repeat one more time? Or understood? Understood but not absorbed? What is it?
One more time.
So you know so many versions of us, sir. Our state of being, learner state of being, so many versions.
No, just it's a two-line matter. Don't worry about it.
But that is the real situation, sir.
Yeah. No problem. I can repeat many times also. Only thing that I want you to
No,
understand.
we understood, sir.
Oh,
वो
okay.
क्या हम लोग भी लिख करके try करेंगे तो it will work out.
Okay. Yes.
General idea we understood. We have to maximize the class SB and minimize the SW.
In the projected space, not the original space.
Yeah, in the projected space.
Sir, I will repeat. Okay, so please follow it. So here, till here, what we are saying is that we want to find out V. So that is everybody is clear with. V is the line direction onto which we want to project. So we want to find out the line direction where the distance between the classes is more and the scatter within the classes is less, right? And so we are trying to solve for that V and we have arrived at this problem. And we said that If you can find out the eigenvector of SW inverse SB, then we are done. That is the optimal V, because it's an eigenvalue problem. So now I'm coming and saying that you need not even do that much. You can simplify it further. How do you simplify it? There is one important property for SB. By using that property, you can simplify it further. Okay, so the property goes like this. When you multiply any vector, okay, any vector V with SBV, that will be pointing in the same direction as mu1 minus mu2. They are just some scale difference, but they will be in the same direction. If SBV is this much, maybe mu1 minus mu2 bar is this much. Or if SBV is this much, then mu1 minus mu2 bar is this much. But all of them are pointing in the same direction because they just multiplied with some scalar. That we are proving here, right? So SB you are expanding. This is equivalent to mu1 minus mu2 times mu1 minus mu2 transpose times x. And this mu1 minus mu2 transpose x is a scalar. All right. So let us take it as a alpha. So alpha times mu1 minus mu2. So this is proving that SBX is in the same direction as mu1 minus mu2. Till this point, is it clear, sir? Is it clear till this point? Who has asked? Parmesha, sir?
Yes, sir.
Clear till this
Yes,
point?
sir.
Yes.
Yes, sir.
So now we want to select V such that when you multiply V with SW inverse SB, we want to get some scalar times V. Okay, for which V that will happen is the question. All right. So let us take this V as SW inverse SB. Let us take this V as SW inverse mu1 minus mu2. So using this property, I said when you multiply, this is a vector. This is also of the same size 1 by d, right? So now when you d by 1. So when you multiply this d by 1 with 1 by d, what will you get? What will you get, sir? Sorry. This is not d by 1, 1 by d. Sorry for that. Okay. So here, when you multiply this with the SW inverse mu1 minus mu2, right? When you multiply this with SB, using this property SBX, this is in the same direction as mu1 minus mu2. It means this whole thing can be written as alpha times mu1 minus mu2. Am I right, sir? Because this is also the same thing as this because the whole thing, this SW inverse mu1 minus mu2 is equivalent to the dimensions of the x, right? So for any vector x, so this SW inverse mu1 minus mu2 is also some vector. What happens when you multiply this vector with SB? It will be in the same direction as mu1 minus mu2. So instead of writing this thing, so I'm just writing this, replacing this with SW inverse alpha times mu1 minus mu2. Can I do it, sir? Using this property that we have proved here. Can I do it, sir? Yes. So
Yes, sir.
now this can be written as, if I bring this alpha outside, this is alpha times SW inverse mu1 minus mu2. Okay. So what is this SW inverse mu1 minus mu2, sir? Isn't it the V that we took here? Isn't it the V that we took? Right.
Yes.
And this is alpha is some scalar. So it means we are getting this in this format, SW inverse SBV is equivalent to some scalar lambda times V. So here lambda is equivalent to alpha, V is equivalent to SW inverse mu1 minus mu2. So it means what? V is equivalent to SW inverse mu1 minus mu2. This is the optimal V. It means you just have to compute the means in the original space within class scatter matrix in the original space, multiply them, you will get this V. That is what the simplification that we are providing for this. Is it clear,
Okay.
sir? Clear now?
Okay.
Yeah. So you need not even solve the eigenvalue problem. You directly got V. V is this. This is the optimal V. So let us solve an example. You will get an idea. So here is an example. There are 5 samples from class 1, 6 samples from class 2. Okay. So can you compute the mean of class 1 and mean of class 2? Mu1, mu2, SW. These 3 things are required because V is equivalent to SW inverse mu1 minus mu2. Okay. You see that for this example, if you project the data points onto a direction of maximum variance, there is no clear separation between them. So if you apply principal component analysis, all right, let us try to apply this linear discriminant analysis. What is the linear discriminant analysis? It is finding out the line direction V where there is a clear separation, and the optimal V is SW inverse mu1 minus mu2. So what is mu1? Mean of class 1. What is mean of class 1? 1 plus 2 plus 3 plus 4 plus 5 divided by 5. Isn't it 3? Correct me if I am wrong. I think that is 15. 15 divided by 5 is 3.
3 is yes.
15 by 5.
Yeah, 2 plus 3 plus 3 plus 5 plus 5. What is the total? 10, 16,
18 by 10.
18 by 5.
3.6.
3.9.
6.
3.6 only.
6 only. Okay. Okay, 3.6. So 3 comma 3.6 is mu. Mu1. Can you tell me mu2? Three plus 3, 6, 6 plus 3, 9 plus 5, 14
Yes.
plus 6, 20. 20 divided by 6.
6.
3.33.
3.
Yeah. Is it 33 or 6? 6, 20 divided by 6. 33 only, right?
3.33.
And what about this other dimension? 0, 1, 1,
2.
4, 4 plus 7, 7, 2, right? 12 divided by 6, 2. Right? So this is mu1, 3 comma 3.6. This is mu2, 3.3 comma 2. Now, what else we need? We need SW. SW equivalent to S1 plus S2. Scatter 1 plus scatter 2. And scatter 1 is n minus 1 times the covariance. N1 minus 1 times the covariance of class 1. And scatter 2 is n2 minus 1 times the covariance of class 2. Right? So that is what is computed here. So there are total 5 points in the class 1, 5 minus 1, 4 times covariance of C1, which is the scatter 1 matrix. Similarly, scatter 2 matrix is n minus 1, which is the 6 instances in class 2. So 6 minus 1, which is 5 times the covariance of C2, which is this. So take the sum over this, S1 plus S2, you've got this. So now compute the inverse of SW, inverse of this, you've got this. So now what is V? V is SW inverse mu1 minus mu2, which is this. This is the direction of the vector where this is happening. So now once you get V, how do you compute the projected data points? V transpose x1, V transpose x2, so on, V transpose xn. Am I right? Right. So multiply this V transpose C1 transpose. This is the V that we got. These are the original data points. Okay. And these are the projected data points, minus 0.98 to 0.48. And similarly, to get the projected data points of class 2, we've got this V transpose C2 times V transpose C2 transpose, which is minus 0.79 to, this is a V, optimal V that we've got. Multiply them with the class 2 instances. So you will get minus 0.79 to minus 0.31. So please notice here that there is a clear separation. All these are the positive points, all these are the negative points. So there is a clear separation. You can see that line also here graphically. There is a clear separation between the points, positive points, and the class 1 instances and the class 2 instances. So I hope that is clear with this example. there are some mistakes in the slides. I've corrected them. Okay, so I've shared the updated slides only after corrections.
So this line is showing us the projected points now, sir.
This line, I mean, after projection, you will get the points here. Here, all these are the
Okay.
blue points, and all
So,
these
but
are the.
the in the actual this thing, the points are somewhere else. So when you're dragging the points to the projection, there will be some loss, right?
Yeah,
So
yes, some
when
information
you're
loss
bringing
would be.
from that dimension to this
But
dimension.
your what is the problem that you are solving here? Classification. It doesn't matter,
Yes.
right, to you?
Okay.
Whatever the feature, it doesn't
Yes,
matter to you.
yes,
You
yes.
want
Sorry,
to,
sir. Sorry.
yes.
I again
No
got
problem.
here. Thought it's a regression.
So whether you will be able to separate them or not is the only question, right? Right.
Yes, sir.
So it means you are simplifying the data, at the same time you are achieving your objective. Both the things are happening, right? Yes. So is it clear?
Yes, sir.
It's a good practice for the mathematical solution for this problem. It's a one of the
Yes, sir.
very good way of learning also. Okay then. So multiple discriminant analysis when there are more than 2 classes, right? So if there are C classes, then you can reduce the dimension to C minus 1 dimensions. All right. So it is the same. So only thing that it will change is that how to compute between scatter distance. Here you are computing it as a mu1 minus mu2 bar, mu1 minus mu2 whole square, right? But here more than 2 classes means there are more than 2 means, mu1, mu2, so on, mu k. There are k classes. So how do you compute the between scatter distance is the question. That is the only difference that you're going to do here. Within class scatter is same, S1 plus S2 plus so on Sk. This will not change. Okay. So this is the sum over all the classes Si. This will not change, but this will change. So you take the overall mean mu, individual means mu1, mu2, so on mu k or mu c. Here it's taken as a c, here we taken as a k, no problem. So now subtract this mu1 minus overall mean mu times mu1 minus mu transpose, multiply this with the number of instances belong to class 1, which is n1. Similarly, mu2 minus mu times mu2 minus mu transpose, multiply this with number of instances belong to class 2 and so forth. Take the sum over all that. That is why that is what between scatter. Ni times, where Ni is the number of instances belong to class I, mu I, which is the mean of class I, minus mu, overall mean, mu I minus mu transpose. Okay, so problem is same. Okay, so this is what you get again when you solve this generalized eigenvalue problem, SBV equivalent to lambda times SWV. Okay, so when this FDA or MDA fails, linear discriminant analysis fails. Okay, so this case where the means are same, when mu1 equal to mu2, then you always get a zero mean, but they are not separated. So here PCA performs reasonably well. So this case, when this is also the case of mu1 equal to mu2, you see that both the means are same. This mean and this mean, both of them are same, right? So here also it will fail. Even the PCA also fails here in this case. The second case when this LDA fails is that when J of V is always larger. So this is the mean, this is the mean, right? It is always larger. Whatever direction you choose, it is always larger. This case also LDA fails, even the PC also fails. So that's all. Thank you very much and happy learning. If you have any queries in the theory, I will take. Otherwise, we will move to this implementation part. I hope you understood and followed it.
Yes, sir.
Same thing again, import the required libraries. Here we are implementing 2 algorithms, principal component analysis and linear discriminant analysis. So here is a PCA. I'm importing it from sklearn.decomposition, and discriminant analysis, I'm importing it from sklearn.discriminant analysis. I'm just naming it as LDA as the name is big. Okay. So the first step is done. The second step is load the data set. Here we are loading iris data set. Iris data set, you know, right? It's a flower data set. There are three classes: iris setosa, versicolor, virginica, and there are four features. Yeah, sepal length, sepal width, petal length, petal width. Okay, prepare the data set X and Y. Access dataset dot data, you will get X. Access dataset dot target, you will get Y. I'm also accessing dataset dot target names to get the column names. That's sepal length, sepal width, petal length, petal width. Okay. So now we are building the model. Here I am calling the PCA, which we have already imported, and number of components equivalent to 2. It means number of dimensions we are reducing it to 2. From 4 to we are reducing it to 2. So now I'm calling this object PCA, whatever that I get here, model, that dot fit on the X and transform X. You can break it down into two steps also, PCA dot fit, PCA dot transform, but directly I'm doing PCA dot fit of X dot transform of X. So this is the X in the reduced dimension, just naming it as a XR. This is X after transforming into two-dimensional space, or after projecting it into lower dimensional space. So this is the reduced X underscore R. I am fitting LDA also. LDA, calling LDA with the number of components equivalent to 2. So this is the object that I get LDA. Fit X comma Y. Please notice the difference. You're just passing X here. You're also passing the target values here. Right. So it is the kind of unsupervised learning here. It's a kind of supervised learning here. Although both of them are dimensionality reduction techniques. So here we are using the label information also in case of LDA. Whereas in PCA, we are not using any label information. All right. Please notice that difference. Okay.
Yes, sir.
So transforming X. So this is the reduced X. I'm just calling it as a X underscore R2 to distinguish between PCA features and the LDA features. So let us plot them. Both this reduced X in the scatter them in the lower dimensional space with the two features. Okay, so we have used different colors for the different classes. As there are three classes, we have taken three colors: navy, turquoise, and dark orange. Okay, some colors. Okay, so we are just naming them with a different, I mean, labeling them, not labeling. We are representing them with the different colors based on their group label. So for all yi equal to I equal to 0, 1, 2, it means there are three classes. For each class separately, we are scattering them with the different colors. Color is chosen from here. So you can see this. Okay, so similarly, I am plotting the LDA features also, X underscore R2. Here I am plotting the this PCA features. Okay, so you see that this is a PCA. In the projected space, there is no clear separation in the projected space, in the two-dimensional space. Whereas if you see LDA, there clearly there is a separation here. I mean, much better than this PCA, as and the classes are well separated even in the projected space. All right. Whereas you see that here there is a completely mix of points, especially this versicolor and virginica data points. Here setosa, versicolor, virginica are the class labels. Flower types: iris setosa, iris versicolor, iris virginica, three flowers. All right. So clear, right? How to import, how to apply, and what is the distance difference between them? Is it clear?
Sir,
Yeah.
so this is the way we have to assess when we do our work, sir. We have to first give it a try with a supervised, sir, normally supervised way of classification.
For
If
assessing.
it doesn't work out, then we have to go with unsupervised. Here, then coming back, our supervised way of separation was only better. Is that
I
so we
couldn't
have to
follow
do?
you. What you asked?
No, sir.
To the
See,
extent that I asked, you are asking about the assessment.
yes, sir, in future, if I take up any problem and I work on
You want to assess
reducing the
whether
dimension.
PCA is better or LDA is better.
No, I wanted to work in a direction of reducing the dimensions. So while working with the dimensions, if I go with the supervised way, generally we do that. Then we go with
No, madam.
unsupervised.
See, it's not like that. Whether supervised or unsupervised, it matters based on the problem at hand. Suppose it's not a classification problem. Why do you apply LDA? Isn't it? PCA is much faster. You can go ahead with that. What is LDA is doing? LDA is projecting that so that the classes are well separated in the projected space. Suppose you don't want to well separate, it's a regression problem. Why do you go for LDA? Not
Because it's
required. It also depends on the problem at hand, not just this. Any other query? Understood, everybody?
Superb, sir. We didn't know that there is so much of depth in this dimensionality reduction which you have shown us with the equations so well.
Thank you. So yeah, we'll wind up the session. Thank you very much, everyone. Happy learning. Now